Alright guys, welcome to your help video here for your Unit 7 study guide. Let's go ahead and get started. I'm going to do the even ones on this video, and I will let you guys do the odds. Alright guys, so here we go. So you'll have a question like this. This is basically just a reducing question, and it has monomials. So when it comes to monomials, you just look at the coefficients and you ask yourself what divides into both of those, and the answer is 7. So you would divide both of those by 7. And the result would be 6/7. And then as for the variables, what we do is we subtract their exponents. So 6 minus 2 is 4. So it's going to be p to the 4th power. And it goes on the bottom because that's where the biggest power was to begin with. Okay? And so your final answer there would be 6/7p to the 4th power. All right, let's go ahead and take a look at our next question here. Number 4. So this is the same question, but with a different type of expression involved. Instead of monomials, it's polynomials. So the way that you reduce a monomial is that you'll need to factor it first. So for instance, on the top, I would need to take out a GCF of 3. And on the bottom, I would need to take out a GCF of 5v first. And after that, I think I'm going to have more to do because it's a trinomial. Oh, this is supposed to be a v, not an x, my bad. And then after that, we do the box method on the trinomial. I made it an x again, darn it. Oh well. There we go. And if you do the box method, you get v plus 2 times v plus 2. So that's the first thing you'll need to do when you want to reduce an expression that involves monomials, is you're going to factor it first. And then after that, all you do is you cancel what they have in common. So final answer here would be 3/5v times v plus 2. And then we're all done. Okay, so for number 6, this one would be repetitive if it weren't for the fact that I want you guys to know how to state the excluded values. I'm still going to simplify it, but there's really nothing new to that. That's kind of like what we've already done. So to simplify it, basically we factor the top and the bottom. So if I factor the top, I get v minus 3 times v minus 7, and that would be a box method. And if I were to factor the denominator, I would get v plus 6 times v minus 3. Okay? And so before I simplify it, though, here's how you state the excluded values. You take the bottom factors and you set them equal to 0. And basically what this means is that v cannot equal 0 because v plus 6 cannot equal 0. And v minus 3 can't equal 0, so therefore v also can't equal 3. These are what we call the excluded values. These are the values that v is not allowed to equal. Okay? Now, so that's the main thing I wanted to focus on for this. Is finding those excluded values. It's where the vertical asymptotes or the holes would be located. But we'll finish the problem anyway. It says simplify. So to simplify, you just cross off what they have in common. But that part is not quite as important as this because we've already done one of those other ones already. So the point there is the bottom can't equal 0. All right. So let's go ahead and take a look at number 8. Simplify the expression. So this example is just to help you guys know what to do whenever you're multiplying rational expressions. First of all, you could think of that as being over 1. And then you just do the top times the top over the bottom times the bottom. Now, we don't really need to put times 1 on the bottom. That doesn't really accomplish anything. But on the top, we do need that 3 there. Now, I'm not going to actually multiply these together, though, because when we're multiplying, you're going to have to factor anyway to reduce. So, for instance, on this one here, I could take a 10 out of that. And for this one here, I can take an 8 out. So let's do that. So I have 3. And if I take a 10 out, there's going to be a 10 here with a v minus 2 here. And then on the bottom, if I take an 8 out, that's going to leave 2 minus v here. And like I said, I'm not going to include the 1 because we don't really need it. Now, here's one thing. These, we talked about these factors here. They're opposites. And so you can cross these factors off if you put a negative in the front. Okay? So that leaves me with negative 30 over 8 because I multiplied the 3 and the 10 together. And then, of course, after that, we'll need to reduce the monomials there. So 2 goes into the top 15 times, and it goes into the bottom 4 times. And that would be our final answer. So the steps are basically put them together into one fraction, factor, and reduce and or cancel. Okay, so let's go ahead and move on to number 10. So now this is an example for division. When it comes to division, we do same change flip. So same, in other words, keep the fraction the same. Change the division into multiplication, and then flip the second fraction over. After that, it's a multiplication problem. So it's top times top over bottom times bottom. Now, once again, we're not actually going to multiply them together because what we want to do is we want to factor and cancel. So on the top, I'm going to take a 4 out. I don't really need the 1 in the front, by the way, so I'll just get rid of that. But I'm going to take a 4 out, which would leave me with this. And on the bottom, this is a box method problem. So if you were to factor that problem with a box, you would end up with n here, and a negative 8 here, and a positive 9 here. So after that, you go ahead and cancel what you can. So these go away, and this goes away. Since we have nothing on top, we're going to put a 1 on the top as a placeholder. And on the bottom, we have n plus 9. So there's our final answer. So your steps for division are keep, change, flip, factor, cancel. Okay? So now we're moving into addition. In order to add rational expressions, they need to have a common denominator. So the first step is to factor those denominators. So on the bottom left, that cannot be factored, so it's just going to stay the same. But the bottom right can be factored. 2v minus 2, that can factor into 2 times v minus 1. And now that it's factored, we're going to go ahead and try to match up their factors. So after you factor the denominators, we want to multiply to match those denominators. So this one has a v plus 3, and the one on the right has a 2 and a v minus 1. So the fraction on the left side, it needs a 2, and it also needs a v minus 1. The fraction on the right side needs a v plus 3. Okay? After you have gotten them to have a common denominator, we need to simplify the numerators, which is usually a two-step process. First, you're going to have to multiply. So 2 times 3v is 6v, and then we're going to distribute that into these parentheses here. to give us 6v squared minus 6v. We will not be multiplying on the bottom. We're just going to go ahead and leave those separate because it makes our last step easier if we do that. On this one up here, we're going to distribute this 6v into the parentheses, which is going to give us 6v squared plus 18v. And then the next step to simplifying these expressions is to combine those numerators into one. So 6v squared minus 6v plus 6v squared plus 18v all over the common denominator of 2 times v plus 3 times v minus 1. And then from there, we're just going to go ahead and combine our like terms. This 6v squared and this 6v squared is going to make 12v squared. And the negative 6v and the positive 18v is going to make 12v. And sometimes at the end, although not very often, you're going to have to reduce. So on the top, I see I could take a 12 out, actually a 12v. And then after that, we're going to reduce. Now, I don't see any factors that'll just cancel, but I do see that I can reduce the 12 with the 2. And so that'll give me 6v times v plus 1 over v plus 3 times v minus 1. Okay? And there we have it. Let's move on to number 14. It's another problem, pretty similar. This is subtraction instead of addition. But steps are pretty much the same. We still need a common denominator, so step 1 is to factor the denominator. Now in this case, neither one of those denominators is factorable, so we're going to leave it just like that. But we are going to move on to the second step, which is to multiply to match. So I'm going to multiply the left side by 2x plus 5. And then I'm going to multiply the right side by x plus 1. So that's the end of step 2. Step 3 is to simplify the numerators. So we're going to multiply into the parentheses first. And then we're going to combine the numerators together into one. In this case, this is where the difference happens because we're subtracting. You need to distribute the negative into the parentheses. And that's pretty much the only difference that happens when you're subtracting as opposed to whenever you are multiplying. So if I take that negative and distribute it into the parentheses, this 3 is going to come out negative. And this 3 is going to come out negative. And after that, we just combine the like terms and stick with what we were doing before. So 12x, take away 3x is 9x. 30 combined with negative 3 makes 27. Now, the top can be factored, so you can try to factor it, but in this case, I don't think that if I factor it, it's not going to cancel anything out, and that's usually what happens. So like I told you guys when we did this lesson, a lot of times you'll just stop here after you put the numerators together and just kind of see if your answer is already there. Because going through the work of factoring to see if you can reduce is a lot of times with these types of problems, completely unnecessary. So, all right, so that is number 14. So go ahead and take a look at 16. It's a complex fraction. So when we're doing complex fractions, the goal is to make it into a simple fraction. And the way that we do that is by multiplying the top and the bottom of the big fraction by the denominators of the little fraction. So in this case, I would multiply the top and the bottom by 9. That way, that cancels, and it leaves me with just x squared on the bottom. And I'm allowed to do that so long as I also multiply the top by 9, which would be 27 over x. Now that's a little bit simpler. We still have a little bit of work to do here because it's still not a simple fraction, but it's a more simple fraction. To make it a perfectly simple fraction, I would need to fix that fraction on the top there. So I want to get rid of that little x in the denominator. So I'm going to multiply this guy here by an x over 1, which is allowed so long as I also multiply that x on the bottom. And sometimes you can reduce these at this point after you've turned it into a simple fraction, but in this case it doesn't reduce, so we're good to go right there. All right, let's go ahead and take a look at another one of these, number 18. Sometimes your complex fractions have more than just 2 little fractions inside of them. Sometimes they have 3. They could have 4 or more, but I'll only be giving you either 2 or 3. So, okay, so how do we deal with this? Well, let's say you wanted to get rid of this little 5 here first. Well, that's fine. I'm going to go ahead and multiply the bottom here by 5, which will leave me with 1 in the bottom, which is pretty sweet. And then on the top here, I'm going to multiply that by 5 also, but you've got to multiply it by both of these. So it's going to be 9 over a squared times 5 over 1. And it's going to be 3 over a squared times 5 over 1. And sometimes if you're lucky, something here will cancel also, which will save you a little bit of work. But in this case, nothing cancels, unfortunately. So I'm left with 45 over a squared plus 15 over a squared. And now I want to get rid of that a squared. So the way that we do that is we want to multiply by a squared, right? But once again, if you're going to multiply this one by a squared, you have to multiply everything by a squared. And so in this case, the a squares cancel here, they cancel there, and we're left with 45 plus 15 over a squared, which is combining to make 60 over a squared. Now some of you guys might have noticed along the way that this problem could have been done in a much simpler way. And if you see those ways, then go for it. But I wanted to stick to the steps I gave you just in case you end up with one that doesn't have those convenient little shortcuts. But if you didn't notice them, then don't worry about it. The steps will work. But the idea is basically just to multiply by those little denominators until you end up with a simple fraction. All right, so number 20, we are going to solve an equation with rational expressions. Now, whenever you're doing these, a lot of times you'll want to factor the denominator first once again, but in this case we don't need to because they're monomials. Anytime you work with monomials, that's not necessary. So all we need to do is multiply by the denominator. So I'm going to multiply every one of these fractions by 5r squared. Oops, changed my color, sorry about that. Okay, so we're going to put that 5r squared on the top of every fraction here now, because we're multiplying it into the top. And I think I put an extra something there. This one shouldn't have had a 5. Erase that. Okay, So after you multiply it, you're going to go ahead and cancel out whatever they got in common. So like this 5r squared and this 5r squared go away. Same thing here. And on this one, just the r squareds go away. So as a result, we have 4 left here. We have 1 left here. And then we have r plus 3 times 5. So that's the end of the second step. So step 1 is to factor, which we didn't need to do. Step 2 is to multiply everything by the denominators and cancel. Step 3 is to solve. Okay, so I'm going to go ahead and distribute a 5 here first. And then I'm going to distribute the negative. All right, I'm going to combine this 1 and this negative 15. And that will give me negative 14. And then after that, we just go ahead and solve old school algebra style there. We end up with 18 here. And then we divide. Now there is another step at the end, easy one to forget, but you want to make sure you do it, is you want to make sure that your answer doesn't make the bottom of your original equation ever make 0. So for instance here, if you were to plug in negative 18 over 5, would that make any of these bottoms equal 0? And the answer is no. So this is a good answer, but every once in a while you may end up with one where you get an answer and it's actually something that will cause the bottom to equal 0. It's what we call an excluded solution or an extraneous solution. Okay, and we don't want those. All right, let's go ahead and take a look at number 22. Pretty similar question, pretty similar. We're going to start by this 1 over 1 here. And I'm going to multiply everything by 5x because I want to clear that denominator out, just like I did on number 20. So 5x here, 5x here, and 5x here. Now in these places it cancels, and it leaves us with 1 minus 3 equals 5x. Then we want to distribute the negative here. Combine the 3 and the 1 there to make 4. Add the x. And we end up with 4 equals 6x. Division will give us 4 over 6, which reduces to 2/3. And once again, just want to make sure it doesn't make your denominator equal 0. This one was a little bit redundant. I was kind of hoping to show you something a little bit more unique because there's really not very much different from this one in number 20. But that's okay. I guess that's how the ball rolls there. Now for your number 23 here, you will have a difference. You're going to want to factor first, okay? So keep that in mind. And maybe there's one more problem that I'm going to do that might demonstrate that. So let's see what 24 is. Okay, so 24 has that. All right, so the first step is to factor. So I'm going to, on the bottom here, I can take out a 3b. And on this bottom, I can't take out a b, but I can still take out a 3. All right, so this one has a 3. This one's got a 3, and this one's got a 3. This one has a b. And then these two both have a b plus 6. So basically, I need to multiply everything by 3, by b, and by b plus 6. And that way, it will cancel out what we need it to. So I'm going to multiply all 3 of these fractions here by a 3, a b, and a b plus 6. And then what we're going to do now is just cancel whatever we can. So like this entire thing cancels this entire thing and leaves us with 4. Here, only the 3's cancel out, and that leaves us with a b and a b plus 6. Here, the 3's cancel out and the b plus 6's cancel out, but I'm still left with a b. All right. So we're going to distribute here. I hate it when there's 6's and b's. They look the same. All right. So now this is a quadratic equation. When you have a quadratic equation, first of all, you want it to equal 0. So I'm going to subtract b on both sides. Second of all, you want it to be in descending order. And what that means is this term should come first because it's the square, followed by the term with just a b, and then the number that doesn't have any variables. Okay? And when you have a quadratic equation in standard form like that, you want to solve it in one of two ways. You can use the quadratic formula or you can use factoring. And my preferred method for solving these is by factoring. So I would use the box method to factor this. And then you take each factor and set each one equal to 0. And then you solve both. There's one answer. And here's the other answer. And once again, you want to make sure that these numbers won't make the denominators equal 0. So if you plug in -4 up here, it's not going to make the bottom equal 0. And it won't do that here either. So -4 is good. And if you plug in -1, it still won't make them equal 0. So -1 works for both either. Now I'm not showing my work for that. But I mean, you guys can check it yourself if you're not too sure. But if you plug those in, you're not going to get 0. So we're good, and we'll keep both of those answers. Okay? All right, let's go ahead and move on to number 26. All right, so now we get into this stuff. Now on your test, these problems are going to be worth multiple points. Okay? It's going to be worth a point for each step you do. Because we spent quite a few days on this. We spent at least three days on getting to the point of doing these types of problems here. So the first thing that you're going to get a point for is describing the end behavior. Okay? So when you do this, you're going to need two of them, one for the left side and one for the right side. And so what we do is we take the front leading terms there, and it's going to be x over -x squared, which reduces to -1 over x. And we talked about this form. When you have that, it comes out to be 0. I forgot my little negative down here. Now, I also gave you guys a shortcut for this. And the shortcut was anytime the top power is less than the bottom power, you could just put 0. So you actually don't need to put any of this stuff here at all. You can, but I just need to see that because I gave you a shortcut for it. All right? And whenever, this is actually going to be my horizontal asymptote. And when you have a horizontal asymptote, whatever it is on the right-handed limit, it's going to be the same thing on the left-handed limit. So they both equal 0. Okay? So that'll be one of the questions that you'll get credit for on this test. I haven't quite decided yet if I'm going to make each of them worth 1 point or maybe just the whole thing worth 1 point. I'm not sure. But for now, we'll just say 1 point each. All right, part B. You're also going to be asked to find the y-intercept. The y-intercept can be found by plugging 0 in for x. And if you do that, anything with an x just goes away. And so you're going to be left with -2 over 2 on the top, which is -1. Okay, so that's another question you'll be asked about these. Now, part C, I'm going to ask you guys to factor on, well, I'm not going to ask you to actually, but you need to know how to factor these. So the top doesn't factor. The bottom does, though. First of all, I would take a -1 out, because and I would encourage you guys to do the same. So if there's a negative in the front, factor that out first. After that, do the box method. So if you do the box method, or it could be a GCF or difference of squares on your test, but the point is factor it. But don't forget, if there's a negative in the front, take that negative out first. But for me, I would do the box after I take out the -1, and that would leave me with this. Okay, now, on your test, I'm not grading you on this. I'm going to put NC for no credit. You need to do it, but I'm not grading you on that at this point in the game, because you'll have already done that a bunch of other times for other problems and gotten credit for it there. But this is important that you do this to answer the other questions. So even though on our steps that I originally taught, I called it part C, I'm just going to put a blank spot there because we do need to do it, but it's not for credit at this point. But the reason we need to do it is so that we can do the other things they ask for, like finding the holes. The holes are where you have the factor on the top and the bottom that are the same, that you can cross off. You take that factor and you set it equal to 0 and solve. And so what we end up getting here is that we have a hole at x equals 2. So that would be worth a point for sure. Forgot to put point there as well. So you'll also be given a point for finding the holes if there are any. And if there aren't any, you could just say none. And if you say none, well, that'll get you a point, so long as that's the right answer. All right, part D, we're asked to find the roots. And that would be worth another point. The roots are where you take the factors that are on the top and you set them equal to 0. But I don't have any factors on the top. So for me, I would say none. In other words, this function does not touch the x-axis anywhere. Part E, you'll also be given some points for finding the vertical asymptote. And that's where you take the factors that are on the bottom and set those ones equal to 0 and solve. So I end up with a vertical asymptote at -1. And then finally, after that, you're going to be given a point for the graph. Now, when I taught this lesson, we talked about plugging in some test points and stuff. You can do that or not. It's up to you. I demonstrated that you don't always have to do that. And if you want to, you can. But you don't have to. The only thing you're going to be graded on your test is whether or not you actually just give me a graph that looks relatively correct. So I see that I have a horizontal asymptote at 0. So I'm going to put an arrow on the right side. I'm going to put an arrow on the left side at 0 because the graph gets flat on the far left and far right at 0 because that's where the horizontal asymptote is. I also see that I have a y-intercept at -1, so I'm going to put a dot here at -1. We have a hole at 2 on the x-axis, but we don't know where that's going to be located just yet, so for now I'm just going to put an h at 2. Then we have our roots, which we don't have any, and then I have a vertical asymptote at -1. Okay. Now, if you wanted to, you could plug in some test points and kind of see what this thing's going to look like. But basically, I would want to see that it hugs the asymptote, it hits the root, and then after that, it gets flat against the horizontal asymptote. And then don't forget, you should have a hole there, so you want to include that hole. All right. Same thing should be happening on the right. We know this one's going to go up because there's no roots on this side. And there's no roots on the other side either. But I knew that that one had to be on the bottom because of this here. Okay. Now technically, I guess this one over here could have been down here. It could have been. And the only way to know is if I do a test point. So I guess on this one, I would need to do a test point. So if I plugged in -2, what would I get? Let me see. I like to use the factored form. it comes out positive. So when I plugged in -2, I got +1. So my original guess was right. It has to be going up so it reaches that point. So if you're ever not sure, you just want to plug in a few more numbers to get a few more points, you can. And usually what I told you to do there is to, if you want to get a good collection of points, you want to pick some numbers that are between every root and every vertical asymptote and whole. But sometimes you can just eyeball it and get a pretty good guess out of it, okay? So now, how am I going to grade this? Once again, I haven't fully decided how I'm going to grade the graph part here. I don't know if I'm going to make it worth 1 point or a few, because it is possible that you guys will get various parts of it correct, but maybe not the whole thing. But for now, let's just say I'm going to grade it as worth 1 point. Okay, let's just say all or nothing. All right, so there is 26. Let's see if I have another one. Here's another one. All right, so this is just more for you guys to see. It doesn't demonstrate a whole lot more, except the very beginning has something extra to it which might be worth looking at. So once again, we want to start by finding our end behavior. Now for these are the ones that you don't have a shortcut for, so you actually do need to work it out. The ones where the power on the top is bigger than the power on the bottom, I didn't have a shortcut for those. So those ones you actually got to work them out. So that would mean we would need to start first of all by saying, okay, so this limit is equal to x cubed over -4x squared. And that reduces to x over -4. And I told you guys also during the course of that lesson that it's probably a good idea to rewrite that as -1/4 x. And then from there, we would use our polynomial worksheet or reference chart to know which way the arrows go. So in this case, we have an odd exponent and a negative coefficient. And since I have an odd exponent and a negative coefficient, my graph will be like this one here. Negative coefficient, odd exponent, looks like that. So on the right side of my graph, it's going down, and on the left, it's going up. So since it's going down on the right side of my graph, which is what this positive infinity means, it's the right side, and it's going down, my answer is going to be negative infinity because it's going down on the right. And recall that this one stands for right, this one stands for down. That arrow comes from the chart. You don't have to include the arrow if you don't want to, but it's helpful in my opinion. As for this guy, we don't really need to do all this work again because it's all going to be the same. All we need to know is that since we're on the left this time, the arrow is going up. So on this one, it's actually positive infinity on the upside. So there's your end behavior. All right, part B, the y-intercept. Nothing too mind-blowing here. You're just going to plug 0 in for x, which cancels everything with an x out. And I'm left with nothing on the top. And so when that happens, you have 0 over 8, which is just 0. So my y-intercept is 0. Step C, which we're going to black out because step C is factoring. So to begin with, we would start by taking out the greatest common factor, which in this case is an x. And then I would do the box method on what's left. On the bottom, we have another GCF to take out, a -4. And then I would do the box method on what's left. So after you factor, you go ahead and find your holes. And in this case, for holes, there are none. Holes are where you have the same factor on the top as you do on the bottom, and we don't have that here. Part D, looking for our roots. For that, you take the factors on the top and you set them equal to 0. So we have x equals 0, x plus 4 equals 0, and x minus 3 equals 0. So I end up with 3 roots, 0, -4, and +3. Last step, we do the vertical asymptotes, and that's where you take the factors off the bottom and set those equal to 0 and solve. So there's my vertical asymptotes. Now we're ready to go ahead and graph. So here we go. Now you guys can see on the right side of my graph, I'm going down. So my arrow on the right should look like that. So I'm going to draw a downward facing arrow pointing to the right. And on the left side of my graph, we're going up. So my arrow on the left should be pointing up. So I'm going to draw that. So there's my end behavior. We also have a y-intercept at 0, so I'm going to put a dot there at 0. We don't have any holes this time, so we'll skip that. I've got a root at 0, which is the same thing as the y-intercept in this case. I've got another root at -4. And I've got another root at 3. Now I want to find my vertical asymptotes. So I have a vertical asymptote at 2. And I've also got another vertical asymptote at -1. And from there we're going to sketch. And once again, if you want more points to connect the dots, you can. Matter of fact, I think I'm going to need some extra dots here. For the left side of my graph here, I know that it's got to connect this arrow, and then it's got to hit this dot, and then it doesn't cross the x-axis again, so I know it just keeps going down like that on this side. And the opposite happens on this side. It's just going to go up like that. Now in the middle, I'm a little bit confused because there's a few ways that these dots could be connected. I could do this, or I could do this. And I'm not too sure which one it is. Now the only way we can know is if we pick some extra points. So what I'm going to do is I'm going to plug in a number for x equals 1, and that's going to give me another dot to graph so that I can get an answer. So I'm going to plug in 1, and I think that's a lot easier personally to just plug it into the factored form that we have here rather than the original equation. So I'm going to plug 1 into this expression right here. So I'm going to plug 1 in there, and here, 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 and here. And let's see what we get. So that's 5 and -2. So 1 times 5 times -2 is -10. That's -1, and that's 2. So -4 times -1 times 2 is going to be 8. And so I end up with -10 over 8, which is -5 over 4. And when it comes to graphs, it's easier to do this as decimals. So that's -1.25 approximately. So when I plug in 1 for x, the y value I get is -1.25. So that's another dot for me to graph. So I'm going to go over 1 and down 1.25, which would be like right about there. And now I know that my graph can't look like this. It has to be the other one that looks like this. Okay? So sometimes, you'll just need to pick a few more dots to plug in until you get enough dots to where you can connect these things in the appropriate way. All right. I think that might do it for us there. The rest are for you guys to tootle around with and see how you do. But other than that, I'll let you guys go and wish you happy studying for your last test of the semester. I'll see you guys in class later.